Good afternoon, everybody. Let's get started. For announcements, homework 6 is posted. That will be due next week. And for lab, so lab 9, I'm going to postpone that lab to November 15th. So we're not going to have lab this Friday. We're gonna push that 1 week so that I can start the lectures on Internet of Things and MQTT. I think that'll help a little bit to have some background on that. So you can do those labs. So no lab this Friday. I'll send out an announcement about that, and we're going to have lab 9 on November 15th. We'll do that then. So during the previous class, we finished up light sensors, and we talked about and finished up Hall effect magnetic sensors. So today we're going to move on to strain gauges and accelerometers and gyros. Okay, so we're going to connect you more to the mechanical world. We're gonna have this interface, so to speak, between the mechanical world and the electrical world with strain gauges, and then we're going to move on to accelerometers and gyros. All right, so let's start with strain gauges. Let's talk about how strain gauges work. So here's the strain gauge right here. It's sitting on a quarter, so you can see its size as I blow these up in the diagrams in these slides. So they're relatively small. A strain gauge is a device that it's bonded, it's glued to a surface, and it measures strain. And so what is strain? So being mechanical engineers, you know this, but if you have an object length L like this, and you put a strain gauge on it, you can measure strain. And so if you apply a tension on this bar here and it stretches by delta, you can define the normal strain as being delta over L. So that's what the strain gauge is measuring. Okay, here's a zoomed in image of the strain gauge. You can see that there's an insulating back, this insulating kind of substrate here, and then this resistive foil pattern on it with a couple terminals. So the strain gauge is flexible, and you solder to these terminals. You can solder or otherwise connect conductors to those terminals, and then you have this foil pattern here on the strain gauge. So the resistance of a strain gauge changes between its two terminals here as it stretches or compresses in one dimension. So that dimension on this strain gauge would be up and down. That's what it's measuring, the strain up and down as oriented here on the slide. Okay, so here's a diagram of a strain gauge. And the tension will cause the resistance to increase. So you're actually changing the cross-sectional area as you stretch this strain gauge just a little bit. It's just a tiny change of resistance, but it is measurable, as I'll show you. And the compression will cause that resistance to decrease. You're actually bunching up that material and causing the cross-sectional area to increase just slightly. Okay. And so in the other direction, in the other axis, left, right in this case, the strain gauge is relatively insensitive to strain in that direction. So it's really only one axis you're measuring with the strain gauge, in this case, up and down. So strain gauges can be used to measure tensile and compressive stresses, or bending and torsional or shear stresses. So I'll show you some examples of different configurations of strain gauges that can measure those different stresses. But let's talk about how to use them. Here's an actual strain gauge, a photo with a couple wires soldered to the strain gauge terminals there. Resistance changes are very small. So they're on the order of 0.1%. So if you have let's say a 300 ohm strain gauge, you're looking at only a fraction of an ohm, 0.3 ohms or less, that the resistance is changing. So you need some way to measure very small changes. So we're going to have a circuit that detects small resistance changes, but also because we have very small resistance changes and resistive material typically changes resistance over temperature, we need to be able to compensate for resistive changes over temperature of the devices that we're using, either the strain gauge itself or other resistors in the circuit. So what we're going to use is a Wheatstone bridge. So you've probably seen these before. They always look like confusing diamond resistor diagrams in Intro to Circuits class. So this is a Wheatstone bridge. So you have 4 resistors. You apply a source to 2 of the terminals, and you're going to measure a voltage across the other 2 terminals. Okay, so VS is going to be a DC voltage, and VA is a node voltage, VB is a node voltage, V out is the difference between those 2 node voltages, and those are the 2 terminals across which you're going to be measuring this really small voltage change, and then try to measure the strain using that strain gauge. Okay. So let's see. Relative changes in any of the resistor values in this Wheatstone bridge affects that voltage V out. So ideally, you would have R1, R2, and R4 in this case, constant resistances. Okay, that would be ideal. And then R3 would be the strain gauge resistance that's changing slightly, and then you could measure the difference between VA and VB here. Okay, so using voltage division, we can calculate the node voltages of each one of these terminals here, VA and VB. So VA is VS, right? VS is the voltage applied across the series pair of R1 and R2, right? R1 and R2 are in series because VA is an open terminal here. So current that flows through R1 would also flow through R2. So they're in series. You can use voltage division to calculate the voltage VA. In this case, with a ground down here, it's the voltage across R2. So VA is VS, the voltage across R1 and R2 in series, times R2, the voltage across which you're trying to find the voltage VA, divided by the sum of those series resistors. Okay. And likewise, VB is formed by these 2 series resistors, R3 and R4. They have the same current going through them. So VB is VS, that DC voltage, times R4 divided by R3 plus R4. So you get those 2 node voltages. And then you can figure out what V out is. That's the voltage we're going to be using to measure strain, estimate strain. Okay, so VA minus VB is just those 2 expressions, VA minus VB. Plug in these 2 expressions up here. And what you would see if you do that, let's say R3 is a 300 ohm strain gauge. And let's also make those other resistors 300 ohms. So this is a plot of output voltage of this Wheatstone bridge, V out, versus the resistance change. And so you can see I have very small resistance changes here. Here's in percentage. So minus 0.1% to plus 0.1%. And so right in the middle, right where you have 0 resistance change, the output voltage is 0 because that bridge is balanced. And as that resistor R3 changes just slightly, you can see there's an increase in voltage as you apply tension to that strain gauge. Remember, tension is where that resistance goes up. That strain gauge resistance goes up. And in compression, the resistance goes down. Okay, so you can see the variation in voltage versus resistance change and how that relates to tension and compression. So notice that the output voltage is very small. The change in voltage is very small versus the resistance change. So we're going to need an amplifier in this circuit to be able to use that voltage and measure that voltage with something like a microcontroller or even a voltmeter. Remember I said that the raw sensors, the basic sensors themselves typically have a voltage or a current that I call an unusable or hard to use voltage. Right? To create a usable voltage, you need some kind of supporting circuit, in this case, an amplifier. Okay. But the good thing about this circuit is that if all resistances changes, all four of these change by the same percent over temperature, um, the changes in the voltage divider equation cancel out. That means that the temperature change, if the temperature affects all of these resistors by the same percentage, there's no effect on the output voltage. And that's good because then the strain gauge, this whole circuit can get hot, can get cold, and it won't affect the accuracy of the strain gauge measurement. Right? So you can see here each one of these terms, if R1 and R2 both increase by 10%, I'm making that up, 1%, something more reasonable, then that change is going to cancel out. Same thing with R4 and R3. So if all those resistors change by the same percentage, you're good. Your circuit won't be affected, your measurement won't be affected by temperature in terms of estimating strain. Okay. So let's talk about applying these strain gauges to a cantilevered beam here. So you can actually improve sensitivity of measuring bending on this cantilevered beam by using multiple strain gauges. So imagine you have a wall here and then a beam, and you mount four strain gauges. They're all numbered here. So on top, you take two identical strain gauges and you glue them, you bond them to the surface, and you go on the bottom of this beam and you do the same thing with the same strain gauges. Okay, so you have four of those. And then you organize them in the Wheatstone bridge like this, R1, R2, R3, R4, and you're still going to measure the output voltage here, the center two terminals. But now instead of fixed resistors for three of those resistors, you have all four resistances changing based on the strain gauge resistance value. Okay, so all resistances change with bending of this beam here. Okay. And what results is this, that V out actually changes 4 times as much compared to using one strain gauge. Okay, so if I do that same plot, I create that same plot, output voltage in millivolts versus resistance change in percentage, you can see this happen. When I bend that beam down, the voltage goes up. When I bend that beam up, the voltage goes down. And so you can see what's happening here. Look at resistors or strain gauges 2 and 3. So as I bend down, I'm going to be stretching those strain gauges. That means the resistance is going to go up as I push down. So these two resistances go up. And 1 and 4, right, the strain direction causes them to compress and their resistance goes down. 1 and 4 go down there. Okay, so you can kind of see what's happening. One of the node voltages is going up. One of the other node voltage is going down. And that helps the sensitivity here. Right? But you can see there's still only a millivolt or 4 millivolts change in the output. The other plot showed really only slightly above 1 millivolt as it had a resistance change of minus 0.1 to 0.1%. And here you get about 4 times as much. Okay. So you can use this full bridge configuration where you have 4 strain gauges in both of the branches of the Wheatstone bridge, or you can even use just a half bridge. You can use 2 strain gauges if you have to use fewer strain gauges for some reason, or you don't have the area on whatever you're measuring. You can use 2 strain gauges to get improved sensitivity over a single strain gauge. Okay, but if you have higher sensitivity, that requires lower amplification following V out in order to measure with a microcontroller or voltmeter. And that gives you also better noise immunity because there is electrical noise in the environment typically. And so if you can get the signal higher before the amplifier, that means you'll get a higher signal to noise ratio and you'll get a better measurement. Okay. And again, here in this case, if all the strain gauges, if all their resistances change in the same way over temperature, they all change 1%, then those changes cancel out. So this has immunity to temperature changes, which is good. Get a more accurate measurement. Okay. All right. So talking more about how to use them, there are various types of strain gauges. Um, and there are strain gauges that have multiple strain gauges integrated into one component. Okay. So you can have a single strain gauge like I showed you. This is a linear strain gauge. It measures strain in just one direction, just up and down in this case. Here's a half bridge. So you can have two strain gauges on one device that measure in one axis, or you can have a full bridge. Here's a full bridge that measures just in one axis, but you have four of the strain gauges on one device that you can orient or connect together to form a full bridge instead of a half bridge. And you really need to match the strain gauge to the measurement type or the application. For example, if you're measuring bending beams, you can use a double linear strain gauge. Like this is like putting two strain gauges on the top of the beam that I just showed you on the previous slide and two on the bottom, except you only have to use two devices instead of four devices. Okay. In this configuration, you can measure shear, so you can measure strain on torsion bars, for example. Here is a biaxial measurement. This is a 90-degree strain gauge configuration. If you know the principal directions of the strain, you can use this. And then if you have unknown principal directions of the strain, then you could use this rosette configuration. So different configurations, you can read the application notes to show how to apply these. But I just wanted to show you there are different devices with different configurations. Okay, so here's an application example. Let's talk about load cells and amplifier circuits. So you take strain gauges, you put them on some kind of beam or other physical structure, and you can make what we call a load cell, right? This the fundamental component of something like a scale. So this is a single point load cell. You apply this could be, for example, cantilevered here. You attach one side to a wall, a rigid side of a box or something, or a beam, and then you apply the loading here on the left, and you can measure weight with the strain gauges here in the center. This is an S-type load cell that can measure tension or compression. So you could compress this S up and down, or you could stretch it, hang a weight from the bottom, for example, or have a chain up top and a chain out the bottom and measure weight with this load cell. Here are the load cells on a common household scale. If you take a household digital scale apart, you'll see load cells that look like this. You can buy amplifiers that connect to those four load cells. And so one typically is connected to each, or in between the scale platform and each one of the feet, so that if you're off center on the scale and the strain gauges are measuring different weights, you can have one integrated circuit that combines them all together and gives you a total weight on the scale. So they look like that. Okay, here is an amplifier that amplifies the difference between V1 and V2. So here's the Wheatstone bridge with a single strain gauge in the bottom here. In this case, there's a DC source, right? And there's another couple resistors to form another voltage divider here, but probably to set the range. Here's V1 and V2. And this amplifier amplifies the differential voltage using op amps here. So with two op amps and this configuration of resistors, you apply a reference voltage, you apply DC voltage to power the strain gauge, and then you can get an output voltage that gives you the information based on that strain gauge, tells you the strain based on that strain gauge. Okay. There are strain gauge amplifiers with digital outputs. So here's an example. Here's a load cell. There's that bridge again with its output going into one of the inputs here. There's a multiplexer. Here's a programmable gain amplifier. Here's an built-in analog to digital converter, 24-bit sigma delta converter. That's another type of ADC. So this ADC has pretty high resolution, right? 24 bits, that's a lot. And then you have a digital interface which takes that digital value and formats it so that that data can go out over a serial connection to a microcontroller, okay, from the microcontroller unit there. And then there's some supporting electronics. There's an analog voltage supply regulator here that keeps the voltage constant on that load cell or sets the voltage on that load cell. Here's a voltage reference here, probably for that ADC, and an oscillator that that runs that ADC and any kind of control going on there that needs a clock. Okay, but this chip, this integrated circuit, lets you connect just a load cell without any complicated interface, and then it gives you access to digital data already amplified, already sampled, that you can read with your microcontroller. Okay, so that might be useful for future projects. You could take strain gauges and you can use them in pressure sensors. So let's suppose you're trying to measure the pressure in some kind of vessel, or you have a compressor tank and you want to measure the pressure, or come up with an application. I used one of these to measure the vacuum pulled by a radon fan in a home radon mitigation system. Okay, so common pressure sensors use strain gauges on a diaphragm, and when that diaphragm deflects, the strain gauges can detect that. So you can see over here, if I have strain gauges on this diaphragm and then I apply pressure on one side, you get this bulging out of the diaphragm here. And one strain gauge here, that will be under tension. The other one here will be under compression. And so you can use those two possibly in a half bridge to measure the pressure. You can calibrate that strain to pressure. And here's an Adafruit board with one of these pressure sensors already on it. Okay. Here's another application, tire pressure management system like you have in your car. If you have a car that shows you your tire pressure is low on your instrument panel there, it might be one of these devices in your tire. So you can see here's the Schrader valve here and the stem that sticks out of the tire. Here's the tire boundary. This is inside here. So you have a pressure sensor port here. There's a pressure sensor port. And then you can see there's an antenna here that transmits wirelessly to outside the tire. And you could read the car's computer can read the pressure of the tire. Okay, so another application of a strain gauge. So common pressure sensor strain gauges are resistive or piezoresistive. So piezoresistivity represents changes in resistance. I'm sorry, so piezoresistive devices, their resistance changes in two ways. The resistivity changes of that piezoresistive material, in addition to the cross-sectional area changing of that strain gauge. Okay, so that's a different type of material. So two types of automotive tire pressure management systems are available. Just to show you an application here, direct TPMS is what this is. It's actually measuring the air pressure of the tire. So direct TPMS uses the air pressure sensor in each wheel to determine tire pressure. And then there's the neat approach of using indirect TPMS. So you can use the ABS wheel speed sensors. Remember, we talked about that during the last lecture when we talked about Hall effect sensors. You could accurately measure speed, or even as I'll call it the phase between tires. As one tire rotates a little faster and gets a little ahead of or behind of the other, you can use those speed sensors to detect lower pressure of a tire rolling at a different speed. Right? If you have a lower tire pressure, the diameter shrinks a little bit. You can detect that. So that's a way you can actually use a Hall effect sensor to indirectly detect low tire pressure. So clever way of doing it. All right. All right, let's do a clicker problem. So grab your clicker applications. Let's talk about voltage changes in a strain gauge circuit. Okay, so you want to measure the force applied to a cantilevered beam. So here is that cantilevered beam. You're putting a force down on the end of this beam. And you're going to put two strain gauges here, R1 and R3. Those are bonded to the surface. And you're going to configure the Wheatstone bridge like this. You have some kind of DC source. That might be 5 volts, but it's a positive value. And you're going to measure V out. And R1 and R3 are indicated here, right? R1 and R3, top two resistors there. Okay, so what happens to V out when the force is applied? Try to figure out, does V out increase toward positive infinity? Does V out decrease toward negative infinity? Does V out stay the same because they're both here in the top of the Wheatstone bridge? Or can you not tell? Right, so try to figure that out. Okay, so when we push down on this beam, uh, R1 stretches, R3 compresses. So R1's resistance value is going to increase, R3's is going to decrease. So you can model each one of these strain gauges like this in this Wheatstone bridge, right? So VA is this voltage divider right here, R2 over R1 plus R2. So the tension on R1 causes R1 to increase in resistance. And that means by voltage division, VA decreases. So that node voltage goes down. Okay. For the other voltage divider in this Wheatstone bridge, you have VB here. And so R3 in compression, the resistance goes down. Resistance decreases there. Right? And so by voltage division, that means VB increases when R3 decreases. So you have VA going down, VB going up, V out is VA minus VB, right? So you get V out decreasing towards negative infinity when that force is applied. All right. All right. So this is how to visualize what a strain gauge is going to do and how its resistance is going to change as you put it on something like this beam and apply a force. All right. So that was strain gauges. We can measure strain. All right. But let's take a look at accelerometers. So accelerometers and gyroscopes. So accelerometers measure acceleration. Gyros typically measure rates of turn. And let's talk about how they work. So accelerometers typically detect a small amount of movement of some kind of proof mass. And that proof mass is attached to some kind of spring structure. So this is a cartoon that shows some kind of base that's fixed, and then a spring, a coil spring. It's usually not a coil spring, and then a mass. So if I were to, let's say this base is something that I'm going to accelerate to the left, you'd imagine that the mass would stretch this spring to the right, and if I move the base to the right, the mass would compress the spring. So if there's a way to detect that electronically, we can measure that acceleration. And there's usually one accelerometer per axis. So if you're measuring acceleration in 3 dimensions, an X, Y, Z axis, then you have 3 accelerometers. And there are common types, here are 3 common types of accelerometers, of electronic accelerometers. There's MEMS capacitive, right? Microelectronic mechanisms. I forget what that stands for, MEMS. But MEMS and piezoresistive accelerometers and then piezoelectric accelerometers. So MEMS capacitive look something like this. So the capacitance in here changes as this proof mass moves. Okay, so when the plates of the capacitance right here, you can see in this cartoon, this diagram here. Um, thank you, micro electromechanical systems. I deal with electromagnetics so much that whenever I see EM in something, I want to say electromagnetics, but someone shot out in the chat micro electromechanical systems. Thank you. But as the proof mass moves here due to acceleration, the plates that you can see here get closer or farther away, and that capacitance changes. So capacitance changes with acceleration. These devices are small, they're low cost, and they're typically used to measure low frequency motion. So like if you have avionics where something's moving slowly, changing bank, or if you have your phone where you're relatively slowly changing the orientation on your phone so you can get a portrait uh, portrait photo instead of a landscape photo. You could use MEMS capacitive. Piezoresistive accelerometers work like this. You can see here's a diagram of the proof mass. Here are the piezo resistors on this, again, this kind of cantilevered beam that bends. Here's the base. And that resistance changes with deformation due to acceleration. Okay, so if you move this up or down, if you move the whole unit up or down, that beam is going to bend because of the proof mass. You can measure the resistance of that piezo resistor there. These are typically used in higher bandwidth applications, meaning if you have to measure more rapidly changing acceleration, like you can measure vibration, you can do crash detection, you can do high G shock. Something's again changing, the acceleration is getting very high or changing rapidly. You can also use these in to measure the effect of explosives. Piezoelectric are the most expensive here. And so piezoelectric material develops a voltage across two of its faces when compressed. So unlike piezoresistive, whose resistive properties change, we're actually generating a voltage here when we compress that piezoelectric material. And these are typically used in high sensitivity test and measurement. So you have more expensive on the right, low cost on the left, and you choose based on your application. And you'd look into the data sheets and see what kind of performance you need to meet your specs. All right. Here's a picture. This was a cool picture I found on the web. You can go to this website, watch this video. I took some screenshots here. It was a good example of a cross section of this device. So you can see there are terminals here. That's where you would connect the capacitor. And then here's a proof mass, so this can move, and it's attached to these capacitor plates here. And so those capacitor plates get closer or farther away based on the acceleration. Here's an electron microscope view of the capacitor plates of a device. You can see the gap and the plates. And on the left and the right, those are the terminals to those to the capacitor, which has many fingers that are interleaved here to form that capacitor. Okay, let's talk about how to use them. So here's an example accelerometer. This is a 3-axis accelerometer built into an integrated circuit. So it's X, Y, and Z here. So here's the chip. You can see you apply VDD and ground, and it actually has a few external connections for analog to digital converters. But the acceleration data and the ADC data comes out over the serial line here. Okay. So you can take this device, here's that device on a board, and connect it to the serial ports of a microcontroller and apply power, and you have an accelerometer with a digital output. Here's what's inside here. So this is a micromachined silicon structure. So it has suspended silicon structures inside, anchored to the substrate of the integrated circuit. So here are the capacitors here, um, right there. And so those capacitances, change as the proof mass moves. And so displacement of that proof mass causes an imbalance in the pairs of capacitors. And it's only by a few picofarads. So that has to be detected here. And that imbalance is measured using charge integration in response to when you apply a voltage to that capacitor. So you apply a voltage, you measure the charge, you can determine the imbalance of those capacitors and figure out how much that proof mass has moved. Right, and then so this mux selects which axis. You have X, Y, and Z axes here. The mux selects multiplexer, selects the axis. Here's the amplifier, and here's the ADC, the analog to digital converter. So that gives a digital value of what of the charge, basically the charge imbalance there. The control logic takes that ADC value, formats it so that it can go out over the serial line. And when you request that data from a microcontroller, that control logic will give you the values. And you can see there's a temperature sensor here for temperature compensation and just other ADC inputs here, and some peripherals here, including a clock that runs the circuits. So that's a neat little accelerometer integrated circuit. You can find a lot of these. You can find accelerometers and gyros built in to many different integrated circuits. You have one in lab on your board. So let's move on to gyros. So how do these gyros work? So gyros sense rotation, electronic gyros sense rotation using these integrated circuits or more complex electronic devices. So here's a plot. You can go look at the plot and information behind this at this reference here. But here's size, small and large. And here's the size axis, physical size of the gyro. And here is a drift rate. Right? So 1 degree per year, 1 degree per day, 1 degree per hour, 1 degree per minute. And you can see the different applications here of these three different types. So on the small and higher drift rate or worse drift rate range, right, are these MEMS gyros. And they use various techniques. One of those techniques is vibrating arms, and those vibrating arms react to the Coriolis force, and then you can sense the deflection of those arms to measure the gyroscopic rate. Okay, and then there are much more expensive gyros like the fiber optic gyro and the ring laser gyros. They look like this. Okay, and they basically use counter-propagating beams, beams going in different directions. One direction maybe clockwise, the other counterclockwise, and they propagate with different time delays based on the rate of the gyro, and you get a shifting interference pattern. And so you can see these here, and those are for space vehicles where you have to have a very low drift, very high quality gyro. Okay, most of what we see in our consumer electronic devices are these up here, the lower cost MEMS gyros. So here's an example structure. This is actually an older gyro, but I really like the picture just to kind of show you, like here's the proof mass, and you can see the interleaved fingers here and how this works as you rotate about an axis that probably comes straight up and down here. It's kind of an angled axis here, or angled view here. But that's a neat view into a MEMS device that was probably pretty modern in 2009. Okay, so you can take accelerometers and gyros and integrate them into what we call an IMU, an inertial measurement unit. So this is what you're working on in lab. And so modern IMUs use electronic accelerometers and gyroscopes to provide information to determine position, and attitude. So you don't want to get into this attitude unless you intend to, but you can measure um, XYZ uh, axes for the gyro rates. So current day systems that require attitude information are typically moving over to electronic IMUs versus spinning physical gyros. In the legacy approach, you may have seen inside one of these. Here's a gyro that senses pitch and bank. So you can see there's a roll gimbal, a pitch gimbal. Here's the gyro. Here's the spinning weight, spinning mass in here, and that's connected to an indicator that gives you a position on an artificial horizon. But now we're moving to more modern approaches that have electronic gyros. They give you the same information, but lower weight, lower cost, more reliable. And on your Arduino board, you have a 6 degree of freedom IMU. And there are a few microcontroller boards that have these different types of chips. And so you can get acceleration, XYZ, and gyroscopic rates around the XYZ axes. Okay. All right. So I hope that gives you a feel for how to connect accelerometers and gyroscopes and how they work, and maybe some considerations we'll talk about in lab on drift rates and how you compensate for drift rates. We're going to talk about algorithms in lab, and you're going to use one in lab that compensate for offsets. These gyros typically have, electronic gyros typically have some kind of bias or offset. When you integrate that rate with that has an offset, you're going to get a drift in angles. And so we're going to talk about ways in lab that you can mitigate that and build a more reliable gyro. All right. So I think before diving into the next topic, I'd like to end this here. So let's close here. So don't forget, homework 6 is posted. It is due on November 13th next week. So take a look at that. Let me know if you have any questions. Lab 9, I have postponed until 11:15, and that will let us get into the Internet of Things and MQTT topics. That's where we're going to connect your project to Wi-Fi, connect it to a network, and be able to publish and subscribe information using MQTT. So you'll be able to control your project and get sensor data off your project over a wireless network through an MQTT broker. We'll talk about that. Check Canvas for all of the upcoming assignments and lectures and labs that are posted there. I will hold office hours in just a few seconds, so if you'd like to join, please join. If not, I'll see you next time. Have a great night.